Today's problem is path with minimum effort, difficulty medium. You are given a 2D array mat of size n times m, n by m. Your task is to find the minimum possible path cost from the top left cell, 0, 0, to the bottom right cell, which would be n minus 1, m minus 1, by moving up, down, left, or right between adjacent cells. Note, the cost of a path is defined as the maximum absolute difference between the values of any two consecutive cells along that path. Okay, I think that could probably be laid out a little better. I mean, so the title here is path with minimum effort. We're not really looking for the path with the minimum effort. I took the first example and tried to figure it out, and adding up the cost to move from cell to cell, and then looked at the output. The output is 4. I get something like, well, I got a much bigger number than 4. And what we actually want here is a path that minimizes the maximum effort between adjacent cells. Okay, so the maximum effort between adjacent cells here is, well, there's a couple of them. One is moving from 7 to 3, the effort is going to be 4. Moving from 2 to 6, it's going to be 4. And we could actually go from 6 to 10, 10 to 8, that's still 4. We couldn't go from the 1 to the 10. But that's it. We're looking for the minimum maximum. Now this one, let's see. This one, if you can find a path with the same number all the way through, then the minimum maximum effort is 0. It's interesting. The path actually looks like a 2 also. Constraints, let's see, n and m dimensions of the matrix will be between 1 and 100. Contents of the matrix cells will be between 0 and 10 to the 6th, 1 million. All right, expected complexities, come back to that in a minute. Graph, topic tags, graph, depth first search, breadth first search. I'm not sure how a depth first search would come into play here. Shortest path problems. The first algorithm that comes to mind is Dijkstra's algorithm. Complexity of Dijkstra's algorithm. It's a graph algorithm, but we can work with a matrix as a graph. The time complexity is O of E log V. E is number of edges, V is number of vertices. If we use a priority queue to for vertices, then every edge relaxation is going to require a priority queue operation. And we'll come back and talk about what relaxation means, but there's E edges, and a priority queue operation takes O of log V. So E times log V, since there are E edges, relaxation of an edge means that if we're considering an edge from U to V, then we test whether the shortest distance from the source to V is not the direct path from source to V, but rather going from source to U and then from U to V. And if that's the case, then we update the data structures. Okay. I guess I should probably add that Dijkstra is a single source algorithm, which is what we have here. We're given a starting point. So, okay. I prefer to, create classes for these problems, but in this case, converting that matrix to a graph doesn't seem to really be a convenient way to do it. I mean, each cell is analogous to a vertex, but the cells are not numbered, and we would need to exhaustively enumerate the effort to go from each of those cells to every adjacent cell before we can even start on the algorithm. So let's skip that. We are going to create a class, a cell class containing row, column, and effort. That effort is going to be the maximum effort required to reach that cell. Let's probably scoot this over a little bit. Okay, yeah. Not the effort from the source to the cell, but the maximum effort encountered to reach this cell. Okay. Min cost path. So we'll get the row count, we'll get the column count, we'll create a distance matrix storing the minimum, maximum effort to reach cell ij, and initialize it to a big value because we're looking for minimum value. So we want to be sure that the first distance that we find is smaller than the distance that we initialized it to. All right, priority queue. We're going to have a priority queue for cell objects. Those are going to be ordered by effort. Now, the terms that we use for the term that we typically use for edges, is weight. What is the weight from edge? What's the weight of the edge from, let's say, U to V? But that can really represent anything: cost, distance, time. In this case, effort. So, yeah. In any case, that's a part of the Dijkstra algorithm, is ordering the vertices in order, in increasing order of weight, or in this case, effort. So we're starting at 0, 0. So the distance to get from 0, 0 to 0, 0 is 0. And we've got to start by adding a cell to the queue, and that is our start cell at 0, 0 with an effort of 0 to get there. This we use to navigate to adjacent cells. And let's see, how much of this can I get in here? I want to be able to see everything at once. I want to be able to see the, I guess we're not going to be able to see the drawing, but we can still see the numbers here. All right, keeping in mind that while the queue is not empty, every time through this loop we are going to pull the first cell from the queue, and we're going to set R to the row, C to the column, and current effort to the effort. All right, I think if we get to here, that's really all that we need to be able to see. All right. Oh, wait a minute. You know what? I can scoot that over a little bit. Yeah, that's fine. That's fine. And then if I scooted that over far enough, you can probably see, you know what? Let's just leave it like that. The only thing that's really not visible here is this return -1 at the end. We're never going to reach that. but Java requires a return statement for every possible path. So if we were unable to find a path, then we would drop out down here. If we emptied the queue without finding a path from the top left to the bottom right, which is really not possible in a rectangular matrix, we would drop out here, and we got to return something. Actually, what we want to return is, once we have reached the destination cell, we'll return the current effort. Okay. So I think that's enough. I need to, oh, you know what? That's not so good either. I need some room to draw stuff here as well. So let's try it right there, and I'm going to pause this and sketch something out. Okay, so we can start here. We've got a distance matrix. The distance from 0, 0 to 0, 0 has been initialized as 0. Everything else in here, the blank squares, are initialized to integer max value, so a very big number. And in the priority queue, we've got one cell, and that is the cell at 0, 0 with an effort of 0. So we remove that from the queue, and we set RC current effort down here. Is current effort 0 greater than the distance? 0. No, it isn't. Are we at the destination? No. All right, so now we have to start looking at adjacent cells. So we look up, there's nothing there. Down, yes. Down, we're going from 7 to 3. So the effort is going to be 4. New max effort is the max of the current effort, which is 0, or effort to neighbor, which is 4. Is the new max effort less than what's currently in the dist matrix, which is a very big number? So yes, 4 is less than that. We're going to put the 4 in there. Okay, now again, this just gets carried forward from cell to cell. I mean, nothing is cumulative when we're talking about the effort. It's just cell to cell. All right, and we offer the new cell, which is what? 1, 0, and 4. So that goes into the queue. 1, 0, and 4. All right, so we did up, down, left. Okay, we go to the right. That is a 2. Effort to neighbor would be 5. That is greater than 0, so new max effort to here would be 5. All right, let's see, 0, 5, and then offer that cell to the queue. So that would be 0, 1, 5. 0, 1, 5. Good. All right. We're done with this. This is off the queue now. The next cell to come off the queue, and again, these are in order by effort. So, so what is the word I'm looking for? Fortunately, it's not the right word, but the cell at the top of our simulated queue here is actually the one that we want. It would be at the top of the real queue. So we'll take that. We're working on this now. 1, 0, 4. All right, 1, 0, 4. Current effort of 4. Is that greater than 4? No. Are we at the destination? No. All right, so now we start looking up. All right. Max effort. Well, max effort here is going to be 4, but we already, it's not going to be less than what's already in there, which is 0. So that doesn't help us. Up, down, there is nothing down, left, no, right. Okay, what if we go to the right? Then we're going from a 3 to a 1. All right, 3 to 1. So that is 2. Effort to neighbor is 2. Max effort is the max of 4 and 2. So that's 4. So what goes in here is 4. Again, that just gets carried forward. We're looking for maximum effort, but we're looking for the minimum of the maximum effort. So that can't be a 2 because the path to get from the source to that cell, there's already an effort of 4. So the 4 gets carried forward, and we add that cell, which is 1, 1, 4. 1, 1, 4. All right? And we're done with this one, right? Okay. Done. Next cell, because we have to take these in order of effort. So this is the next one that we take. We go to 1, 1. With a 4 is the current effort, which is 4 greater than the distance. No, it's the same. We're not at the destination. So now we start looking adjacent. We go up. All right. Going up, the distance is from 1 to 2, so that is 1. The new max effort is the max of 4 and 1, so that is 4. Is 4 less than what is currently in that cell, which is 5? And it is less. So what we're going to do is replace the 5 with 4. Okay, place the 5 with 4 and put that cell in the queue. And that is 0, 1, 4. 0, 1, 4. Okay, so we went up, down, nothing is happening there. If we go from 4 to 3, nothing is going to change. Well, wait. Max current effort. No, it isn't going to change. The max effort is still 4. If we go to the right, we're going 1 to 10. Okay. So effort to get to the neighbor is 9. New max effort is 9. And we're going to put this in here. 9. And we offer to the queue 1, 2, 9. 1, 2, 9. Okay, we're done with this. Next, we take in order of priority 0, 1, 4. Right, which is here, up, nothing. Down, down. If we go down, we're going to have an effort of 1, so that doesn't change the maximum effort. Up, down. If we go this way, we have a maximum effort of 5, which is not less than 0. So we're not going to put that in there. If we go this way, we're going from 2 to 6. That is a 4, so that's a tie. So let's see if so the new max effort of 4 actually is less than what's in there. So we'll put a 4 and offer 0, 2, 4. Okay, 0, 2, 4. All right, and we are done with this one. All right, the next one that we take, that 4 unfortunately looks like a 9, but it's a 4. we take the smallest effort, that's a 4. So now we're at 0, 2, 4. Okay, we go up, there's nothing. We go down. If we go down, the max effort, like 6 to 10, is 4. So the new max effort is 4. And is that less than, is that less than 9? Yes. So the 9 is gone. And in its place, we have a 4. All right, so we went up, down, left. Left, we're going from 6 to 2. That's still a 4, so that doesn't change anything. If we go to the right, we have 6 to 5, so that is a 1. So that doesn't change the max effort. So we are going to propagate. Oh, did I add that? Oh, I didn't add that. I gotta add that to the queue. It's 1, 2, 4. 1, 2, and 4. All right. So this is our max effort is still 4, and that is less than max value. So 4 goes in there, and we add that 0, 3, 4. Okay, 0, 3, 4. All right. It's a tie here as far as which one we take next, this one or this one. This one we are done with. But either way, 10 to 8 is 2. 5 to 8 is 3. That isn't going to change the max value. So that is going to end up as 4. We put it in the queue. When we get to it, and what would we put in there? We would put 1, 3, 4. Okay, so let's say we just did that one. This is not changing anything. We get the destination and we return 4. Okay. So that's how the maximum minimum gets propagated through the matrix. Let's get rid of all of the drawing. Let's send this back over here. Let's go ahead and submit. Okay. Okay, that's it. Again, it's a shortest path problem. When you see a shortest path problem, the first thing that you think of is Dijkstra's, or I should say a single source shortest path algorithm. Dijkstra is the first thing that should come to mind. You may need to modify it a little bit as we did in this case. Yeah, if you anticipate showing up at an interview where you're likely to be asked a question about graphs and or shortest paths in a matrix, you'll need to know that. So do a little research on Dijkstra's algorithm. It's a nice algorithm. It's not a difficult algorithm. It's pretty intuitive. So that's it. And oh wait, I forgot to say, please like the video, subscribe to the channel, the notifications, and we'll see you next time.